Okay, sample problem 3.9. Combustion of a 5.50 gram sample of benzene produces 18.59 grams of carbon dioxide and 3.81 grams of water. Determine the empirical formula and the molecular formula of benzene, given that its molar mass is approximately 78 grams per mole. Okay, so the first step is to find the empirical formula. This is a combustion problem, so we know that the sample has a mass of 5.50 grams. And then after we undergo combustion, so here's the idea. The benzene I'll write it as CnHm, assuming we don't know what the formula is going to react with oxygen. Remember, oxygen is a diatomic element, so it's O2, not O, to form carbon dioxide and water. That's the combustion process, okay? So now what we do is we say, okay, the amount of carbon dioxide that's produced is 18.59 grams, and the amount of water that's produced is 3.81 grams. So from that information, we want to find the empirical formula. Okay, so here's what we'll do. We'll take one of the products at a time. 18.59 grams of carbon dioxide. And we're going to find the number of grams of carbon that are in 18.59 grams of carbon dioxide. So it's 12.01 grams of carbon, that's the molar mass of carbon, over 44.01 grams of CO2. Okay, let me make that a little bit bigger here so that it's not so scrunched up. Okay, 12.01 grams of carbon over 44.01 grams of CO2. By taking the mass of carbon dioxide that's produced in the reaction and multiplying it by the ratio of how much carbon weighs to how much the compound weighs, the molar mass of the compound, that will give us the mass of the carbon that was produced. So 18.59 times 12.01 divided by 44.01, and you get 5.073, 5.073. Okay, so that's the number of grams of carbon that was produced in the reaction, but that's also the number of grams of carbon that was in the original reaction right here. So now we know the mass of that carbon. Now we do the same thing for the water. The water, it's much smaller mass, 3.81 grams of water. Now, water has two hydrogens, so it's 2 times 1.01 grams divided by the molar mass of water. Okay. So that is going to give us the mass of hydrogen that's in 3.81 grams of water. So 3.81 divided by 3.81 times 2.02 divided by 18.02. 2.02 is 2 times 1.01. 0.4271. Okay? So what we now know is that in that compound that reacted, the benzene, the mass of hydrogen in that benzene sample was 0.4271. Okay? Now you can actually check that because they tell us in the problem that the mass of the benzene was 5.50 grams. If you add these two masses here together, you're going to get about 5.50 grams. Okay? Works out nicely. Now, what we want to do in the next step is to take the masses of carbon and hydrogen and convert them to moles of carbon and hydrogen. And the reason will become apparent once we do that. So let's go through that exercise. 5.073 grams of carbon. Conversion to a mole divided by the molar mass of that element. Okay, so 5.073 divided by 12.01. 0.4224. Okay, now we do the same thing for hydrogen. The mass of the hydrogen was 0.4271. We're going to convert that to moles. Okay, 0.4271 divided by 1.01 is 0.4229. Now, if you look at those two number of moles, they're pretty much the same. They're very close to each other. Ratio, it looks like it's about a ratio of 1 to 1. But here's what we'll do in the next step. We're going to take those moles. A chemical formula, whether it be an empirical formula or a molecular formula, these should be whole numbers. And if we take the n to m, that's going to be a ratio. And that ratio should be either 1 or 2 or 3, so forth and so on. Okay, so we're trying to get whole numbers out here. So here's what we're going to do. Imagine this. Imagine that we had 20 women and 4 men. And we wanted to find a ratio of women to men. 20 women divided by 4 men. That would give us a ratio of 5, right? The ratio is really 5 to 1. There's 5 women for every 1 man in that ratio. So what we did was we divided each of these numbers. 20, we divided that by 4. And then we took 4 and we divided that by 4. And that gave us 5 to 1. That's the ratio. So we're going to do exactly the same thing here. We're going to take each of these two numbers, 0.4224 moles of carbon, and we're going to divide it by the smaller of the two. The smaller of the two is the carbon. And you get 1, right? Obviously. There's 1 carbon for every carbon in the molecule. So now we can write that 1 as a subscript. Now we'll do the same thing for the hydrogen. How many hydrogens are there per carbon? Well, those numbers are very, very close to each other. In fact, if you run them through the calculator, you're going to get a number that's 1.00 something. It's 1. It's essentially 1. So that means the ratio of carbon to hydrogen is a 1. So there we go. Now we wouldn't write it as C1H1, we would write it as CH. If the subscript is a 1, we don't write it at all. And there is your empirical formula. Okay? So we ran through that problem. Find the empirical formula of benzene. It appears to be CH. There's one more part of this question, which is we want to find the molecular formula. And to find the molecular formula, we have to be given an additional piece of information, and that is given here. That's the molar mass of the compound benzene. The molar mass, it says, is 78, approximately 78 grams per mole. So we need to know that. 78 grams per mole. That's the molar mass. Now, just to show you an analogy, imagine I said this. Imagine I said, hey, we have this train, and this train has several cars on it. And I'm not going to tell you how many cars are on there. But what I'm going to do is I'm going to tell you that each car weighs the same. And each car weighs 10 tons. No, let's make it bigger than that. Let's make it 100 tons. All of them are 100 tons. And then I tell you that together the train weighs 2,000 tons. And then I ask you, how many cars are there? Here's what you could do. You would say, okay, it's 2,000 tons. And one car weighs 100 tons. And if you did that ratio, you would find that it's 20 cars. 20 cars adds up to 2,000 tons if each one weighs 100 tons. So we're going to do the same thing here in this problem. The compound benzene has a molar mass of 78. Then we ask, okay, here's our empirical formula, CH. CH weighs how much? Well, carbon weighs 12, hydrogen weighs 1. Notice I'm being very round in those numbers, and the reason I'm being round, I'm not using 12.01 and 1.01, is because benzene is not given out as 0.0 something. If it were, I would use the point something something for the C and the H. CH together weighs about 13 grams per mole. So just like the train, if the total weight is 78, in this case it's the mass, 78 grams per mole, and I say that one CH weighs 13, okay, here's what you would get. 78 divided by 13 is 6. So that means you have 6 of the CHs. Now, we don't write it as 6CH. We write it as 6 times 1. 1 is the subscript. And 6 times 1. So we get C6, H6. Just like with the train, we would say that it's one of these, but you've got 20 of them. Okay? So subscripts. This is the molecular formula. Okay? So what you do is you take the given value, the molar mass, you figure out the molar mass of the empirical formula that you've already calculated, take the ratio of those two numbers, 78 over 13. That'll give you a nice whole number, like 6, and then you multiply that by the subscripts that you had in the empirical formula. So let's say the empirical formula had been CH2. You would get times 6 would be C6H12. And there you go.